Okay, so now we're going to look at some real AP problems. This is from 1993. It says a car of mass m, initially at rest at time t equals 0, is driven to the right as shown above. Okay, and it says the car encounters a resistive force equal to negative kV. It's like we had before, except instead of B, we have K. Same thing, just using a different letter. And now we want to know, A, the dot below represents the center of mass of the car. Draw and label vectors to represent the forces acting on the car as it moves with a velocity v to the right. Okay, so this is what this should look like. It says as a velocity v to the right. They're not necessarily saying that it's at terminal velocity, but it is moving. And so here is the force of the car, which we can call F naught, constant force. That's it pushing to the right, F naught. The resistive force is kV. Don't forget the force of gravity. And then equal to the force of gravity but opposite in direction is the normal force. That's it. Now let me tell you something about the AP test. Each open-ended question is worth 15 points. And those 15 points are distributed to the different parts of the question. So this part A, if you do this, that's 3 points. You've already gotten 3 out of the 15 points just for doing a good free body diagram. Right? Make sure the arrows connect, etc. Follow the rules. That's it. So now we want to know the horizontal acceleration of the car in terms of kv, f naught, and m. Okay. So what does that look like? Well, if we're determining acceleration, we're going to have to get that from Newton's second law. And so the sum of the forces, so this is F, what direction is the acceleration going to be? The acceleration is going to be backwards, right, in the direction of the, because it's going to be slowing down. Or no, it's not. Sorry, it's speeding up. This is speeding up. So the change in acceleration is in the other direction. But this is speeding up, so it's in the direction of F naught. So I'm going to do F naught minus kV equals ma. So I want to find the acceleration. Well, the acceleration is F naught minus kV over m. And that's it. That's all we have to do. That also was worth 3 points. Right? So if you did the free body diagram correctly and you did this correctly, then you've got 6 points already out of 15 on this question. Okay, C, derive the equation expressing the velocity of the car as a function of time in terms of K, F naught, and M. Right. This one gets really tricky. This one involves the crazy calculus. So what happens is this now becomes, let me rewrite this. Except instead of A, I'm going to write dv dt. So this is F naught minus kV over m. Okay, and so now, how am I going to get a function for velocity? Here's what we have to do. What we have to do is actually separate these. I'm going to keep v on this side, and I'm going to put t over on this side. Right, so I'm going to have, I'm going to bring this, since this thing contains v, I'm going to bring this over, so I divide. So this is going to be m over F naught minus kV dv equals dt. So how do I get from dv to actually be v and t to actually be t, right? Some function involved there. Well, what I have to do is integrate. So I'm going to integrate this side from 0 to some velocity, some later velocity. And here I'm going to go from time 0 to some later time t. In calculus, you're not really supposed to do that. But here, we're putting in variables because we want an equation expressing the velocity as a function of time. So we're going to have a changing time. What is this final time? We don't know. What is this final velocity? We don't know. And so this is easy to integrate, right? This would just be t. But this looks pretty weird, right? How do we do this? What we have to do is we have to think of this as backwards chain rule derivation, right? It's the antiderivative, but we've got like something inside of another function. And so it's like using the chain rule. Now I know that the derivative, the antiderivative of 1 over v is natural log of v, but that's not going to work here because I don't just have v, I have this whole thing. But if I can get this as one variable, then I can do that. So let me take this, F naught minus kV. I'm going to set this equal to just U. Okay, so now I've got F naught minus kV equals U, so I can plug U into this. However, if I plug U in here, then I don't have the V. I've got dV. So I need to replace dV with something. So I go back down here, and I'm going to take the derivative of this with respect to V. So du dV, I take the derivative of this with respect to V, I end up with negative K. That means that du, or negative 1 over K du, is equal to dV. Now I can substitute this in for dV. Right? This will go in here, and this will go in here. So what does this new thing look like now? From zero to V, whatever that later V is going to be m over U. Right? And now I'm substituting this thing in, so this is negative 1 over K times du equals integral 0 to t of dt. Let me bring this thing out in front. Notice now I've got negative m over k. Does that look familiar? Negative m over b. So that's interesting. Integral from 0 to v of 1 over u du equals integral from 0 to t of dt. Let me move up here now. Now I can do this. I know this is natural log of u. Right? So this becomes negative m over k, natural log of u, from 0 to v. And then this is equals, this ends up just becoming t. Sorry, that shouldn't be that simple. It would be this, from 0 to v. Now I'm going to bring this over to here. So I've got natural log of u equals negative k over m times t. Now how do I get rid of a natural log? Right, the way I get rid of this is that I exponentiate both sides. I put both sides to the power of e, right? So e to the this thing is just u. So u equals e to the negative k over m times t. But what was u? U is equal to this thing, right? F naught minus kV. So this is F naught minus kV. I'm still going, by the way, from 0 to v. Or rather, let me plug this back into here before I do anything else. Sorry. So natural log of, this is going to be F naught minus kV from 0 to v equals negative k over m times t. So if I do natural log of, I plug v into this, F naught minus kV minus natural log, if I plug 0 in, then I just end up with F naught equals negative k over m times t. Subtraction, though, means I can put this over this. So I get natural log of F naught minus kV over F naught equals negative k over m times t. So this can go out of there, and this just becomes natural log of 1 minus k over F naught times v equals negative k over m times t. Good. Now what I'll do is I'll take both sides, e to both sides. Oh yeah, okay. Let's see how this works. So this becomes 1 minus k over F naught times v equals e to the negative k over m times t. So I'm going to subtract 1 from this side, or rather, if I leave it, k over F naught v equals, I'll do 1 minus e to the negative k over m times t. And now I bring this over, so v equals F naught over k, 1 minus e to the negative k over m times t. That's it. That's my function now for velocity as a function of time. That was a lot, right? I realized that, but look at what we started with. Differential equation. All we did was we substituted in for u. So we substituted in for this thing and we substituted in for this thing. So it's backwards chain rule, right? Now I simplify it, I integrate, and now all I'm trying to do is plug v back in here and then solve for v. So I do all this stuff, and I'm using a lot of my math tools. If it was tricky, here's what I would say. Put this away and then try it again. Look back to help yourself, because it's just going to be this same process again and again. The reason we have to use the u substitution, by the way, is because I've got a function down in here. Right? Why do I have this function? Because I have a constant force on the car that's pushing it forward. Right? So then that's worth 5 points. All of this is worth 5 points. Worth, parts D and E down on those other slides, these are worth 2 points each. All right, and what do these look like? For part D, they want the car's velocity as a function of time. So we saw that coefficient in the very front was f0 over k. So it looks like that. That's velocity as a function of time. The other one asks for the acceleration as a function of time. And it says label the important values. So this is f0 over m. That's the initial acceleration. Because when we plug 0 in for the velocity, then a is just f0 over m. And this looks like this. The acceleration is going to 0. So 2 points, 2 points. Let's take a look at another question here. So this is a question from 2000. By the way, this 1993 question was Mechanics 2. That means it's the second question. Usually they get harder. So the first one's the easiest, second one's the next hardest, and then so you can see what the level of difficulty is sometimes. But again, you're not doing new stuff. It's like the same process you've done over and over. So now a rubber ball of mass m is dropped from a cliff. As it falls, there is air drag. The force is bv squared. So that's the drag force, bv squared. It's not kv like the other one we had before. The drag coefficient b is directly proportional to the cross-sectional area of the ball. So this is like what we did in the first lesson. And as the ball falls, its speed approaches a constant value called the terminal speed. Okay, so now we need to do a free body diagram. It says draw and label all the forces the instant before it reaches terminal speed. Some instant before it reaches terminal speed. So some instant before terminal speed, that means this resistive force arrow is less than this force of gravity. It hasn't reached terminal speed yet. That means this is not the same length as this. Okay, so now state whether the magnitude of the acceleration increases, decreases, or remains zero, remains the same as the ball approaches terminal speed. Here's the idea. Since sigma f equals ma, mg minus bv squared equals ma. Initially, at time 0, the acceleration is just equal to g. But as time goes on and this gets faster and faster, that means a gets less. This value gets more. This whole thing gets less. That means a has to get less. So a decreases over time as v increases. And you can use some argument like that. Again, this is 3 points. This would be worth 3 out of the 15 points. C says write but do not solve a differential equation for the instantaneous speed of the ball in terms of time t, the given quantities, and fundamental constants. All right, so now I'm taking this and I'm turning this into a differential equation. The differential equation means it's like dv dt. That's it. So this is mg minus bv squared over m equals dv dt. That's the differential equation. It says do not solve it. Solving was that other thing that we did with the previous example. So done. D, determine the terminal speed v in terms of the given quantities and fundamental constants. So at terminal velocity, so what is this, part D now? At terminal velocity, that's where the acceleration is 0. So mg minus bv squared equals 0. So I'm solving for v. So v is equal to mg over b, and then the square root of that. So that's it for that one. And it says determine the energy dissipated by the drag force during the fall if the ball is released at height h and reaches its terminal speed before hitting the ground in terms of given quantities and fundamental constants. All right, so now we're going to use GAPC. Right, so we've got K plus U plus the work done by non-conservative forces plus the work done by applied forces equals the kinetic energy at the end and the potential energy at the end. So initially there's no kinetic energy, there's no work done by outside forces, Earth, but that's part of the system, so that's in here. And then there's work done by non-conservative forces, that's what we're looking for because that's what the air resistance is. And then when it hits the ground, there's no more potential energy. Right? So what is our potential energy? It's dropped from height h, so this is mgh, plus the work done by non-conservative forces, equal to, and then I want to know the final, so this is 1/2 mv term squared. Right, that's the terminal velocity. But notice I solved for that here. So that's going to be kind of nice. So the work done by the air resistance is going to be 1/2 m times this thing squared. So this is mg over b. And then minus mgh. So the work done by air resistance, I can bring out an mg. And then I've got, so this is now another m over 2b minus h. And that's it. Okay, so using GAPC now in solving a problem like that. All right. This next one we have a block of mass m. Initially it's moving with a velocity. So it's moving with velocity v0 at time 0. And then there is a resistive force on it, given by kV. And how much work must be done to bring the block to rest, etc. Okay, so here's the idea. The block initially is moving this way, v0, but there's this force on it. It's pushing it back that way and slowing it down. So what does the velocity graph look like here? It looks something like this. Right, that's v0, and v0, v is approaching 0. All right. That means that at some later time, it has 0 kinetic energy. So it's starting off with kinetic energy. And K is equal to 1/2 mv squared. So the work done by the friction force is just equal to negative 1/2 mv0 squared. The force is doing negative work. Why is the force doing negative work? Because the force is that way, but the displacement is that way. Right? You think of it that way. And the work is taking away that much kinetic energy. For B now it says that if the force is negative kV, right, so the opposite direction of V and then times K, determine the following. The acceleration of the block in terms of M, K, and V. Right. So here, this is the only horizontal force. So kV equals ma. This is the drag force, and that's equal to ma. Right. This is the force mass times acceleration. So that means that A is equal to kV over m, and that's it. Or the negative rather. Don't forget the negative. So this should be negative here, because the acceleration is in the opposite direction of the velocity. So if we're expressing these as vectors, we include that. Now I want to know part C. It says the speed v as a function of time. So now we need to do this whole thing where this is dv dt equals negative kV over m. All right, so what I'm going to do now is I'm going to bring the v over to this side. I'm going to leave the other things, though, over here. Notice here it's just v. there are no other terms here, right? In the other one, I had the term F naught. Now there are no other terms. It's just this one term. So I'm going to do 1 over V dV equals negative K over M times T. I couldn't set this one up before in the other one. I couldn't set it up like this. But now I can because of this, just having this one term, because there are no other forces here. Right? That's why I end up just with this. So now I have to take the integral from 0 to V of 1 over V dV, and that's equal to the integral of negative K over M times T from 0 to some later time T. This becomes natural log of V from 0 to V, and this is negative K over M T. When I put in, so this becomes natural log of V minus natural log of 0. So this is 1, actually, right? Equals negative K over M times T. E to the what power is 0? Or no, sorry. I'm not going to 0. Aha. Tricky. What's my initial velocity here? My initial velocity is V naught. It's not 0. So this becomes V natural log of V over V naught, negative K over M times T. That's important. Paying attention to what are our initial conditions there. So this now, when I take E both sides to the power of E, or E to the power of both sides, I get V over V naught equals E to the negative K over M times T. So V equals V naught E to the negative K over M times T. Okay, and so that's it. Initially, this thing, if this is 0, that means this whole thing is 1, so V equals V naught at time 0. And then as time goes on, this gets closer and closer to 0. Theoretically, it never actually reaches 0. Right? But in practice, there are things of different grades. The friction force is constantly changing. It does actually reach 0. So this graph looks like, just looks like this. I already drew it. And then the last part, we want to know the total distance that this goes. Okay, if I have a velocity function, how do I get displacement? Well, I get displacement by integrating. So V, now the change in position, so let's say delta x, is from 0 to infinity. I have to go all the way out to infinity where this thing actually stops. So from 0 to infinity, V naught e to the negative K over M times T. All right. So this ends up becoming V naught. I take the integral of this. So in other words, the derivative of what would give me this, it's going to be negative M over K e to the negative K over M times T from 0 to infinity. So let me pull this out. Negative V naught M over K. And now if I plug in infinity into this, then this whole thing, right, this goes to e to the negative infinity is just 0. Right, this goes to 0. Oh yeah, because it's getting smaller and smaller. If I plug 0 into that, I get 1. So I get negative 1, so it's just V naught M over K. That's the total distance that it travels. Okay. Again, I realize it's a lot. This is not easy, but it's still this same kind of thing over and over again. So you get used to the process and you do it again and again. And keep in mind when you need to do U substitution. You have to do U substitution when you've got more than one force, right? You've got the resistive force and you've got some other force like gravity or some constant force like we had on the car. In this case, we don't have to do U substitution. Why not? Because there's only one force in that direction, and that's the resistive force.